So as I was saying, like the critical values for a two-tailed test is somewhat different than a one-tailed test, right? So if it's saying that 10% significance level for a two-tailed test, it means 5% of the data is on the left hand side and the remaining 5% should be on the right hand side, right? So two-tailed test for 10% significance level, you will see that the critical value is 1.645, right? But for one-tailed test, I mean the critical value only for 5% could be like 1.645 if we are considering the left hand side, right? That's for like a one tail, and the critical value on the right hand side should be what? On the left hand side should be negative 1.645, and the critical value for the right hand side would be positive 1.645 for a one tail test, right? But for two tail test, you will see that it is always positive, the critical values, right? Because we are taking the absolute value. It's like a modulus. So that way maybe you will know that whether the hypothesis is one tail or two tail. If the hypothesis says that the critical value is negative 1.645, then what should be the type of test or the type of distribution? It could be like a one-tailed normal distribution, right? Because two-tailed is always positive because we take absolute value. So always like we always have to set the null. The golden standard is always take the null as 0, right? If you look through my like my project, I have set my betas as 0, right? Like betas for BMI is 0, betas for smoking is 0, access to clean water is 0. So typically it's 0. It's the standard, but anyone can also choose different values. It's not necessary that you always have to put it as 0. Let's say people want to see the hypothesis where if the average let's say average BMI in the class is 25 or not. So they would set the hypothesis that BMI equals to 25 or BMI equals to 30, right? What's a healthy BMI? How many of you guys are aware of the body mass index? Yes. So if it's like greater than 30, we say overweight, and if it is more than 35, like obese, and so a healthy BMI would be from the range from 25 to 30. Okay, so you can hypothesize, okay, the average BMI in this class is 25 or 27 or something like that. You can set the BMI coefficient equals to 25. Okay, and the t-stat works. We actually check that the beta hat minus the hypothesized value, which is the value you set. Typically I use 0 because I want to see if there is any effect or not. Okay, but not necessarily it has to be 0. It can be any value that you want to set for your hypothesis. So the test works exactly as before, except that the hypothesized value is subtracted from the estimate when forming the statistic. Okay, so this is like a general hypothesis. Okay, a general hypothesis. So let's look at an example. It's the campus crime and enrollment. So an interesting hypothesis is whether crime increases by 1% if enrollment is increased by 1%. Okay, so if like let's say Wayne State we have about approximately, I believe, around 32,000 students in the campus, right? So we want to see if more students are enrolling. That means if, like, let's say additional 1,000 or additional like a few more students, if that is causing more crime in the campus, right? Normally, what would we expect if more students are coming? By probability, there would be a higher chance of committing more crime, right? Instead of 32,000, if there are like 70,000 students, there are more number of people, and the accumulated percentage goes up, right? So, and here they have used both log and log form. Okay, so when it's both log and log form, what's actually the coefficient? The coefficient is actually the elasticity when both are in log form. Okay, so in fact it's a very advantage, like if you can take both log and log form, it can be an advantage because you will get the elasticity directly. Okay, you don't have to calculate the elasticity like separately. So in this case, they have assumed that the null is 1, right? So null is 1, and the alternative is it's not equal to 1. So it's like a two-sided, right? It can be both greater than 1, the alternative, or it can be less than 1. Okay, so in this case, if you see the t-stat is 1.27 minus the hypothesized value that you have chosen. In this case, the hypothesized value is not 0, right? Although the golden standard is, we usually take it as 0, but since here you have hypothesized as 1, so you subtract 1 from the coefficient. So 1.27 minus 1. In the previous cases, we always assumed our null as 0, right? That's why it was 1.27 minus 0 and divided by the standard error. But you can also choose your own value. So in this case, you have chosen that the value should take, the null is 1. Like you're thinking that the log of enrollment should be 1. Alright? And divided by the standard error is in this parenthesis. And we got our t value as 2.45. What is the critical value for 5% significance level? 5% significance level, or 95% like confidence interval. Okay, so at 5% significance level, the critical value is 1.96. That's actually for a normal distribution. That's not for t distribution. But since the n is large, and I have told you guys that if n is greater than 90, the t distribution behaves like a normal distribution. So in this case, do we reject the null or do we accept the null? Our t stat is bigger than the critical value. So what do? We reject the null. That means log enrollment is not 1. It is, maybe it is greater than 1 or it will be less than 1. So in our case, we got 1.27, which means it is greater than 1. So the null is false. We usually do not say something like that, but then we reject the null based on the evidence. Okay, don't use words like it is false or something like that. Okay, tell it in terms of like statistics. Okay, in terms of their language, like false or true. These are like, you know, layman's language. Like we should use like statistical language. So we reject the null because our t stat is greater than the critical value. Right? And since it's a two-tailed test, we take the modulus, right? So you have to take the modulus of this and then compare. So that was for calculating the t-stat. We can also compute the p values, Okay, so if the significance level is made smaller and smaller, so usually if I in exams, if I don't mention any significance value, by default you should assume 5%. Okay, if I don't mention in the question, like you can come up and like ask me that yeah, there's no significance level in this question, that means I want you guys to assume that it is 5% by default if it's not mentioned in the question paper. Okay, but if the significance level is even smaller, let's say 1%, there will be a point where the null hypothesis cannot be rejected anymore, because you would require a higher and higher critical value. The critical value for 5% for a normal is 1.96. Critical value for 1% is 2.5 something, right? Critical value for even smaller significance level would be like, let's say 10 or 100. In that case, we need a very large t-stat to reject the null, right? So there will be a point when the null hypothesis cannot be rejected anymore. Okay, the reason is that by lowering the significance level, one wants to avoid more and more to make the error of rejecting a correct H naught or a correct null hypothesis. So you guys have learned about type 1 error and type 2 error, right? So what is type 1 error and type 2 error? So let's say if the null is true, but by mistake you have rejected the null, right? That's actually you are making like a type 1 error, right? Null is true but you are rejecting. And in another case, the alternative can be true and you are accepting the null. Okay, so something like a patient has cancer and you are saying that that patient does not have any cancer. Okay, which is bad? A patient who has cancer and you are saying that the null is patient does not have cancer, so you are saying that patient does not have cancer. Or is it the other one which is bad, like a patient does not have cancer but you reject the null and say that that person has cancer, and then you give that person chemotherapy. So that is even worse, right? So type 1 error is the worst type of error, like when the null is true and you are rejecting the null and you're saying that yeah, that person has cancer, so let's give treatment to this person. But in reality, that person doesn't even have cancer, so he should not take the medicine at all. Whereas if the cancer patient does not take the medicine, it doesn't harm that person maybe that much, because we are not doing anything to that person negatively. But a healthy person given a chemotherapy, just imagine, or given any kind of medicine, might actually deteriorate the health even more, right? So we want, if you want like a very accurate model, or if you want to say for sure that yeah, our models are really good, then you have to lower the significance level. Like it is even significant at 1% level means that the model is really strong. That means you can tell it for sure that that is happening. Okay, so the smallest significance level at which the null hypothesis is still rejected is called the p-value of the hypothesis test. Okay, this is the critical thing. Okay, so they will give you a p-value. So significance level, lower the significance level, the lower would be your p-value. Alright, so significance level of 1%, maybe the p-value would be like 0.01. In Stata you will see that, right? When we were doing those Stata like last class I did some regression, and we saw that the p, they also state the p value beside the t stat or the z stat. They also mention the p value. Okay, Stata has like all the information, so it's a very useful software. Okay, I'll just. So a small p-value is evidence against the null hypothesis because one would reject the null hypothesis even at small significance level, right? A large p-value is evidence in favor of the null hypothesis. So the small p-value is evidence against, so it's against the null hypothesis, and a large p-value is favor of the null hypothesis. So if you want to reject the null, you want to choose a small p-value, right? Because it's against the null hypothesis, and one would reject the null hypothesis even at small significance level, right? So p-values are more informative than tests at fixed significance levels. Okay, so we will do like an example right now, like how it is calculated. So if you look here, this is a two-sided test, right? And if you look at the area under the graph, it's 0.359 on this side and 0.359 on the other side. So it's like a two-tailed, right? And the p-value is significant at is the significance level at which one is indifferent between rejecting and not rejecting the null hypothesis. In the two-sided case, the p-value is thus the probability that t variables take on a larger absolute value than the realized value of the test statistic. So usually what we do is, when it's a two-sided test, we always take the modulus of t stat, and they have given us the critical value, right? Critical value, if you observe on the right hand side, is 1.85. Critical value on the left hand is minus 1.85, right? But we only look at the positive value because we have taken the modulus of t stat. So we just have to compare the positive 1.85. Okay, in this case the p-value is 0.718. So the null hypothesis is rejected if and only if the corresponding p-value is smaller than the significance level. So only if it falls in this region or that region, right? It can fall on the right hand side region, or it can fall in the left hand side region, and only if the p-value is smaller than the critical p-value. So the critical p-value is 0.0718. Only if it is like 0.06, let's say, that means it falls in the rejection region and we reject the null. So based on our assumption, if our corresponding p-value, that means the way we have like our own t stat or z stat, we should also have our own p-values, right? So if our p-value is smaller than the critical p-value, we reject the null. Okay, so this t stat and p-value are like, you can say they are like complementary. Okay, the way we have like a t stat or z stat, similarly we should have, based on our sample, we should also have a corresponding p-value. Okay, if that is smaller than the critical p-value that they have estimated, like at 0.0718, then we reject the null. So here they said that, for example, for a significance level of 5%, the T statistics would not lie in the rejection region. Why do you think that the significance level of 5% they would not lie in the rejection region? So 5% of T statistics could be, because this area is what, 0.0359, right, on the right hand side, and this area is also like 0.0359 on the left hand side. So 5% would lie here and here. So the rejection region is actually this part, right? 0.039 is here and 0.0939 is here. So when you look at 5% level, it's actually what, 1.96, right? Negative 1.96. Not negative, sorry. For a two tail it would be 1.64 here and plus 1.64 here, right? So it doesn't fall into the rejection region. Is that clear? So if it's at 10%, it would be, for a two tail it will be like 1.28, and 1.28 will be on this side, so negative 1.28. This also doesn't fall in the rejection region, right? So we cannot reject the null hypothesis. So don't worry, like I will be giving you guys like homeworks associated with these problems from the book. Once you guys do the problems, and I will actually upload the solution for homework 3, okay, by this week. So you guys can take a look, like work through the problems, it will get clear, okay? And the videos would be uploaded, so watch them and try to make sense, like if like after doing the homeworks it will become more clearer, right? So guidelines for discussing the economic and statistical significance. So if a variable is statistically significant, discuss the magnitude of the coefficient. Like the for the previous case, what was the magnitude? Like 1.27, right? The coefficient of the log of enrollment. So it's a positive coefficient and it's greater than 1, so it's 1.27. So you should discuss the magnitude of the coefficient to get an idea of its economic or practical importance. If the coefficient is large, you can give some economic suggestions that, yeah, log of enrollment does increase the crime rate on campus, okay? So in that case, what should be the policy suggestion for the school? Should they enroll more students or should they enroll less students? They should be more selective in selecting the students. They should not give admission to just anyone who is just applying, right? So maybe in selective schools, the crime rate is lower, right? Because they attract maybe the not only the good students, but maybe the students that have a less chance of committing a crime. Okay, if it's a more selective school, because they will look through their profile, like their education level. In some schools, believe it or not, they even look at their parents' education. In fact, you get some sort of advantage, like if your parents are from that school, kids get a privilege to get in there. Like especially this is true for the Ivy League schools. They call it a legacy. So legacy is like if your parents went to, like, let's say Columbia, and even though maybe you may not be like maybe you are on the borderline of getting admission, like you are at risk of getting admission, but since your parents have already like they have gone to that school, because of the legacy status, the admission committee would choose you even though you might not be like on the top 10% of their cohort, or maybe you're on the borderline. So that's kind of selection, right? Like a selective thing. So the school knows that the parents were like they didn't commit any crime. They will have all their records. They have their transcript records and everything. So if they are more selective, the enrollment would be lower, right? And selective schools, lower enrollment, so lower crime rate. Okay. So the fact that a coefficient is statistically significant does not necessarily mean it is economically or practically significant. Okay, so this is like again, like how to put that? It's like just because you got one of your coefficients significant does not mean that it is practically, economically or practically significant. So in the first sentence, they are saying that it gives us some idea that it is economic or practical importance. But in the second sentence, they are saying that just because it's significant, it doesn't mean it is economically or practically significant. For example, if our constant is significant, does it have any economic importance? Nothing, right? The constant is not any variable. It's like a constant value. How can that have a economic significance in that case? So you can think like that. Or sometimes some variables like maybe it can become significant in a simple linear regression model, but it could be because that the model is not in the correct form. Okay, it can happen because of multicollinearity, right? If you have a multicollinear model, like one model is influencing the other, then it's a bad model and it will give you like wrong directions. Okay, or if your error term, if it doesn't follow the zero conditional mean, that means the error term is influencing the independent variables. That is also bad in that sense. And a variable is statistically and economically important but has the wrong sign. If you have a wrong sign, then the regression model might be misspecified. Like you are assuming that school enrollment rates, or like if people are getting more educated, their wage would like go up, right? But you ran a regression model and you found that the higher the education you are taking, your wage is going down. That means your model might be misspecified. There could be violation of any of the 5 conditions, the Gauss Markov assumptions. Like it could be error term is not following the zero conditional mean. It could be the independent variables are multicollinear, okay, sort of perfectly multicollinear. Like even if it's like 90% collinear, still it's a problem. Okay, and if a variable is statistically insignificant at 10%, 5% on 1%, one may think of dropping it from the regression. Okay, so you are finding some variables insignificant. You can think of dropping those insignificant variables from your model to get a better result. Okay, if you think that when I was starting my project, do you think that I only started with 5 or 6 variables, or actually did I start with more variables? In fact, I started with 8 or 9 variables. So I was seeing some 2 or 3 variables were not significant. So what I did was I revised the model. So I dropped 1 or 2 insignificant variables from my model and formed a revised form. Okay, and you can actually write that in your paper as well. You can say that we started the model with 8 or 9 variables, but some of the variables were not significant. So we decided that to drop those insignificant variables, and that's the new refined model. Okay, if you look at my paper, on the Dropbox folder. Did I upload my paper there? Okay, I don't think I have my paper, but I will upload my paper as well. So if you look here, actually that was the cross-sectional data. The panel data, I kind of revised the model actually. Okay. So in the other paper, the cross-sectional paper, which is the one actually I will upload, you will see that I have modified my model over there. Oh, you guys could not see it here. Oh, okay. So what I'm going to do now is there's the teaching evaluation, but since only 5 of you guys are here, maybe I'll take the evaluation on Monday, or maybe Monday not a lot of people will turn up because of the break, but let me do something like let me give you guys a quiz because I'll give some extra credit points to all of you guys who are in class. I thought of giving the quiz actually today to everyone,